Welcome to this explainer. Today, we're unpacking the absolute, incredible, and completely invisible journey your voice takes every single time you make a phone call. I mean, think about it. We tap a name, hold the phone up to our ear, and boom, we expect to instantly hear our mom's voice from across the country without a second thought. But right underneath that simple tap, there's this massive cascade of events. We're talking signals flying through the air, computers routing your voice across cities, and protocols that have been quietly evolving for decades. It is, quite literally, an invisible highway of communication.
So, what actually happens the exact second you press call? Well, let's dive right in and look at the step-by-step process that manages to connect you instantly and without a single physical wire between you and the person on the other end. Consider this thought for a second. I was standing in a field in the middle of nowhere, barely one bar of signal, and somehow my call to a friend in another city actually went through. That really hits the nail on the head, doesn't it? It perfectly captures the absolute magic we just take for granted every day. There are no direct physical lines, just thin air, electromagnetic waves, and a whole lot of invisible engineering that's been fine-tuned over generations.
Now, all of this happens in the literal blink of an eye, but we can actually break down the journey of your call into 4 distinct steps, starting right from the moment you begin speaking. First, your voice is digitized. Second, that digital signal gets fired off to a local cell tower. Third, it's routed through a highly complex switching center, and finally, it connects to your receiver. Let's zoom in on step 1.
Okay, so before your voice goes anywhere, it has to change its fundamental form. See, your voice is analog, right? It's made of physical sound waves and vibrations in the air. But network computers, they don't speak analog. So there's a tiny sensor inside your phone called a MEMS sensor that samples your voice thousands of times per second. It's kind of like taking a really smooth, continuous painting and turning it into a grid of blocky digital pixels. Your phone is instantly translating those physical air vibrations into computer code, creating a discrete sequence of zeros and ones. Once your voice is digitized, specific codecs kick in to compress that data so it can be fired out of your phone's antenna as an electromagnetic wave. Imagine literally vacuum packing your voice so it takes up way less space. Now, the exact codec depends heavily on your network. Older GSM networks use something called AMR, but modern VoIP calls, they use EVS, Enhanced Voice Services, which is exactly what gives you that noticeably better high-definition audio quality. So this digital data is compressed, broken down into tiny little packets, and instantly transmitted.
From there, that electromagnetic wave travels straight to the nearest base transceiver station, which is just a fancy term for a cell tower. Think of this action like raising your hand in a really crowded room to say, "Hey, I need to make a call over here." Your phone sends a digital signal to the tower to request a channel. The tower's antennas catch that invisible wave, convert it into light pulses or electrical signals, and instantly pass it down the chain.
And once it hits that first tower, your signal basically starts moving up the chain of command. It bounces from the base transceiver station up to a base station controller, which manages a whole cluster of local towers. And finally, it arrives at the absolute brain of the operation, the mobile switching center.
Now, the absolutely crucial thing to understand here is that the MSC acts a lot like an old-school 1950s switchboard operator, except this operator is a supercomputer handling thousands of global connections in mere milliseconds, using fiber optic lines and radio bridges. It is the central hub. It figures out exactly where the person you're calling is located, starts building a path to get your voice there, and handles all the billing and routing logic behind the scenes.
But wait, this brings up a pretty massive technical headache, right? If your friend is hundreds of miles away, maybe speeding down a highway or walking through a crowded city, how on earth does the mobile switching center know exactly which single cell tower out of millions to send your voice to? Well, the network has an incredibly clever, totally invisible way of tracking them down almost instantly.
You see, even when you aren't on a call, your phone is quietly checking in with nearby towers the whole time. It periodically pings them to register its location. It's essentially whispering to the network, nonstop, "Hey, I'm here, I'm right over here." And fun fact, this is exactly why your battery still drains even when you aren't actively using the device. It's burning energy to maintain that vital lifeline to the nearest tower.
So when you actually press call, the network checks a massive database called the Home Location Register. Think of this like an omnipresent digital address book. Because of all those quiet little whispers we just talked about, it always knows exactly where to forward your call.
It pulls up this info, finds the specific mobile switching center your friend is currently hanging out near, creates a path right to their phone, and boom, triggers their ringtone. And the whole shebang happens in just a matter of seconds.
Now, to really understand why modern calls connect so blazingly fast and sound so much better than they used to, we have to compare the old, dedicated path of traditional circuit switching with the highly efficient packet switching that we use today. Circuit switching is kind of like reserving a private, dedicated VIP lane on the highway just for your conversation. Nobody else is allowed to use it. Packet switching, on the other hand, is much more like carpooling. Your voice is chopped up into small digital packets. Those packets take whatever lanes happen to be free on the network, and then they seamlessly reassemble at the final destination.
And this perfectly illustrates why older networks were so incredibly wasteful. I mean, circuit switching literally reserved that entire VIP lane, even if you were just sitting there in total silence listening to the other person. Packet switching, which is exactly how we route data across the internet and modern VoIP networks today, is way smarter. It only uses network resources when actual data, like your actual spoken voice, needs to be sent. Looking back at the timeline of voice technology, it's pretty wild to see how we jump from Alexander Graham Bell's copper wires to those clunky analog 1G brick phones in the 1980s. Then we got 2G and 3G, which finally brought digital formats, but still largely relied on that older, rigid circuit-switched model. It actually wasn't until the 2010s with 4G that we saw a total paradigm shift in how mobile voice was handled.
And that huge shift? That was VoLTE, or Voice over LTE. And it was a massive game changer. It completely abandoned circuit switching. Instead, it sends your voice as data packets over the 4G network, which is the exact same network your phone uses for web browsing. This is what allows your phone to connect calls in under 2 seconds, delivers that stunning high-definition audio, and, best of all, lets you browse the internet at full speed while you're still talking.
So that brings up a really good question. With all this hyper-efficient, light-speed infrastructure in place, why on earth do our calls still drop?
Well, despite billions of dollars in infrastructure, real-world friction still manages to get in the way of our conversations. Drops usually happen for 3 main reasons. First up is weak signal, caused by physical obstacles. Think about thick concrete basements, or even the energy-efficient glass in big city buildings blocking those electromagnetic waves. Second is tower congestion. During a huge event like New Year's Eve, towers simply run out of available channels. And third, network handoff failures. This happens when your moving car tries to seamlessly transfer your call to the next tower, but just fails at the absolute edge of the coverage zone.
But what if the call doesn't actually drop, but your friend suddenly sounds like a stuttering robot? Well, that is a classic symptom of packet switching called packet loss. Because your voice is broken up into those independent packets of data traveling through the network, sometimes congestion causes a few of them to arrive too late. It's honestly like trying to read a book where a few pages have been ripped out. Your phone's software is desperately trying to guess what those missing words were supposed to be in real time, which gives you that choppy, robotic sound.
Now, as 5G voice-over new radio networks fully deploy, they promise to handle all that congestion much better and reduce latency even further. Tech companies are even experimenting right now with phones that bypass cell towers entirely to talk directly to one another over short distances. It's pretty mind-blowing. And it leaves us wondering, as this invisible communication highway continues to evolve, will the dropped call soon become nothing more than a nostalgic relic of the past? Thanks for exploring this invisible world with us on today's Explainer.